So welcome back. We're going to be talking about some different notations that we use for taking the derivative, as well as the concept of differentiability. So far what we've seen is that what we normally write is f prime of x for the derivative of f of x as a function. And that f prime of x is the same thing as the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. And remember that as h goes to 0 means two things. One, when h is positive, and two, when h is negative. So below, we have a picture of what's happening when h is positive. We have f of x plus h minus f of x being the difference in the height of the two values, f of x and f of x plus h, and h itself being the difference between x and x plus h. And as h goes to 0 on the left, h is negative, so what we can see is that we're going to get f of x minus f of x plus h over negative h to be the slope. But both of them simplify to f of x plus h minus f of x all divided by h. So the symbol prime can be thought of as a special sort of function, right? When you write prime, what you're doing is you're taking the original function and instead spitting out the derivative. So for example, if f of x is x squared, what prime does is give you 2x. It eats x squared and spits out 2x. And if g of x is radical x, what prime does is it eats radical x and gives you 1 over 2 times radical x. And instead of writing f of x equals something and then writing f prime of x equals the derivative, you can just write the function with parentheses and a prime symbol outside. And so x squared prime is the same thing as the derivative of x squared, which is 2x, and radical x prime is the same thing as the derivative of radical x, which is 1 over 2 radical x. And you can take derivatives more than once. Since the derivative takes a function and spits out a function, if you did the derivative twice, you would take the derivative and then take the derivative of the derivative. So what you can see, f double prime of x, using our new way of writing prime, is x squared double prime, which is the same thing as x squared prime prime. And x squared prime is 2x, and 2x prime is 2. And what we call that is taking the second derivative. So we would say that 2 is the second derivative of x squared. So there's other ways of writing the derivative, not just using primes. So we don't always use f of x notation. A lot of times we still write the function y equals x squared. And so instead of writing f prime of x, you could write y prime. Also, you could use big D notation. The big D says take the derivative of what's next. And if you put a letter in the subscript of D, it tells you which letter is the variable to take the derivative of. So we would write something like d sub x of f of x. We could also write d dx of f of x, where d dx stands for the fraction you see there, d over dx. We can also put the f up top and write df dx or dy dx. And all of these are going to be used for different reasons. But the most important thing is to know that they all mean the derivative of f of x. And if you look over on the left in blue, I've written f of x plus h minus f of x over x plus h minus x. And in some sense, you could think of these as what we call delta y over delta x. And delta means change in, right? So it's the change in the y values divided by the change in the x values, which is the same thing we think of as slope. Slope is change in y over change in x, or delta y over delta x. Now those deltas, if you change them to the letter d, d for delta, give you the dy dx notation. And we call that differential notation. Because we call it differential notation, we talk about differentiability. A function is said to be differentiable at a point, x equals a, if the derivative exists. So being differentiable is saying that your derivative makes sense. And you can be differentiable at more than a point. You could be differentiable over an entire interval. Right? We can say that f of x is differentiable for all numbers between 1 and 2 if, whenever you pick one of those numbers, f prime exists for it. And here's something that's a bonus fact right now. The only time functions are differentiable, right, is if, well, in order for the limit to exist, the function has to first be continuous. There's other things that are going on, but if f is differentiable at x equals a, then the function is continuous at x equals a. So if the derivative makes sense at a, then you get for free the function is continuous there. Alright, so the next few slides we're going to compute the derivatives and talk about where these functions are differentiable. So f of x equals x squared is actually differentiable everywhere. Why? Well, if you compute the derivative using the normal method, you see that the derivative is 2x. Well, the nice thing about 2x is it's a polynomial. It exists for all values of x. Since the derivative exists for all values of x, and the original function exists for all values of x, then the function is differentiable everywhere. Now here's g of x as radical x. This is differentiable for any positive value of x. So if we take the limit, and I've gone ahead and I've skipped a couple of steps between all of these equal signs, but go back, review how to take the derivative, we multiply top and bottom by the conjugate, and we cleverly eliminate a bunch of things. And we get that the derivative of radical x is 1 over 2 radical x. And g of x is only defined when x is greater than or equal to 0, right? You can't take the square root of negative numbers. But g prime of x is 1 over 2 radical x. You still can't take the square root of negative numbers, and you can't have 0 in the denominator. 1 over 2 radical x has a 0 in the denominator when x is 0. So we also have to throw out 0. So g of x is defined for 0, but g prime isn't. And so g of x is only differentiable when x is positive. Now here's a weird one, the absolute value. The absolute value is defined everywhere. It's continuous everywhere, it's a nice function. So let's take some of the derivatives. First, let's take the derivative when x is positive. Well, when x is positive and h is really small, x plus h is positive, so you can just get rid of the absolute value signs, and you get that the derivative for absolute value of x is 1 when x is positive. And likewise, you get that the derivative is negative 1 when x is negative. And you can see why by looking at the graph. When x is positive, the slope is 1, and when x is negative, the slope is negative 1. But what happens at 0? Well, when we try to take the derivative at 0, we try to take the limit as h goes to 0. But let's do 0 plus and 0 minus separately. Well, when you calculate it, the derivative on the right is 1, which makes sense because the slopes on the right are 1. And the derivative on the left is negative 1, because the slopes on the left are negative 1. But since those don't agree, we can't say the derivative exists. And so here's an example of a function which is differentiable everywhere but at a point. There's one point that you just can't take the derivative at. And just because the derivative doesn't exist doesn't mean it's not continuous there. Remember, if it's differentiable, then it's continuous, but you can be continuous and not differentiable. and so we say that this is differentiable when x is not 1. So that's it for the video. We have some notations for taking the derivative. We have the concept of differentiability, and that wraps up this week. Next week starts the derivative rules. Go ahead, do the homework with the video, take the quizzes as necessary, and I'll talk to you later.